Okay, so we're looking at problem 11 out of chapter 7. Again, another moment of inertia problem where we have a plate on the top, plate on the bottom, and this W shape, which is W10 by 33. So we've got a W10 by 33. We'll need to get that information from Appendix A. This is a 14 by 1 inch plate on the top. And this is a 12 by 1/2 inch in the bottom. All right. So what we have also is, like normal, we need to start out with a centroid location. So we're going to go ahead and run through that this time just to make sure we're good. And this one's a little different because notice we're gonna put our origin here. So I'm going to work everything off of that. Now, if you think about this, we should be symmetric this way because these are equally aligned. Those are equally aligned. So if one of those plates was kicked one way or the other, we would see that we have a different value. But coming off of this plate, we should find this to be 6 inches over from that origin. Now, because these plates are different sizes and different thicknesses, what's going to happen is this is going to come up a little bit higher. So what we're going to do is determine what the Y bar value will be for the XX axis on this. So we will need to get the depth on this. Should be approximately 10, but let's go see what that is explicitly. We might as well get the area while we're at it. So we're going to go ahead and we're looking at a 10 by 33. So there is our area and there is our depth. It's 9.73. So let's go ahead and go back here and put this information in. 9.73. And the area for this guy was 971. Okay, so we're going to go ahead and we'll call this shape 1 here, shape 2 here, and shape 3 here. And remember, our origin is down here. Okay, so we're going to have shape, we're going to have area, we'll have X, A, X, Y, AY. Okay, so for shape 1, the area is going to be 14 times 1, which is 14. Since these guys are aligned perfectly, the distance over to his centroidal axis from the origin is not going to be half of 14, it's going to be half of 12 down here, so that should give us 6. 6 times 14 gives us 84. So to get to this centroid from the origin, we're going to have a 1/2 inch plus 973 plus another 1/2 inch. So that's going to give us 1073. 1073 times area gives us an AY value of 150.22. Okay, for shape 2, the I-beam, the area, as we just looked up, is 971, and we get that from the chart. So the X would be half of 973, but then we have to come up the 1/2 inch. So 1/2 inch plus half of 973. Oh, I'm sorry, I'm looking at X first. I was just doing Y. So actually, then it's just going to be the same as the 6. Excuse me about that. Okay, so we're going to take that and multiply that. That gives us 58.26. So I jumped the gun on that. So now Y, we're going to do that, what we said before. Half of, or 1/2 inch plus half of 973 would get me to the centroid based on where that origin is. So that's going to give us, when we do that math, 5.365. So again, half of that plus a 1/2 inch. Multiply that times the area, we get 52.094. So area shape 3 is our plate at the bottom. The area is 12 times 1/2 gives us 6 square inches. The x is just half of 12 again, that's going to be 6. So everything, because they're all lined up right like that, that's what we got. So 6 times 6 gives us 36. Y is just going to be half of a half, so that gives us a quarter. A quarter times your area gives you 1.5. Okay, so we're going to sum this, and sum this. So we're going to get 29.71, 178.26, and 203.814. So our x bar, the sum of the ax's divided by the sum of the area, and we should find this to be exactly 6. And when you do that, yes, that's exactly what it comes out to. So you need to think about that. If that doesn't come out to that, then you probably did something wrong. So check that. Y 203.814 divided by my sum of areas. And this one turns out to be 6.8600. So this one's up a little bit above because this plate's a little bit thicker than this. If these plates were exactly the same, we would be right smack in the middle. But in this case, we don't have that going on. So what we're going to do is we're going to put that information on, and then we're going to go ahead and start to do the moment of inertia. Okay, so now that we've determined the location of the centroid, so from that origin, we were 6 over to the y-axis, 6.86 to the x-axis. You know, the depth on our 10 by 33. We know the area, so what we're going to need to determine is the IXC and the IYC. So we need to go back over here. Let's get for the x-axis, for the 33, we've got 171 and 36.6. 171, 36.6. I believe that's all we'll need right now. If we need something else, we'll go back and look at it. So we're going to go in and do our shape. We're going to have our I, X. We're going to have our D, or area, excuse me, area next. Then our D distance, 80 squared. And then ultimately, IX. So shape 1, it's this shape. This is my base. This is my height. So it's 1/12 the base, which is 14 times the height cubed. So it's basically, it's just 14 divided by 12. Doesn't give you much, but you do get 1.167. So not much stiffness. 14 times 1 is 14. So the D distance, now remember, is the distance from the XX composite centroidal axis to the centroidal axis of the shape. So basically, if we took 1/2 plus 973 plus 1/2 and subtract that from this, that'll get us the distance from centroidal axis to centroidal axis. So again, 1/2 plus 973 plus 1/2 minus this. That's our D distance. And we're looking at 3.87. So again, I like to do this because I think that helps you look in which direction you're looking at, okay? So we're going to square that, multiply by that, and we get 209.677. We will add these two together, and we get 210.844. Okay. So most of the stiffness is coming from the fact that this is separated from that axis, and that's exactly what the parallel axis theorem says to you. The further that distance gets away from the centroidal axis of the composite, the more stiffness it's going to give you. So we're going to look at shape 2 now. Shape 2 is our I-beam. So we have the IXC. Okay, so that gives you a lot of stiffness right there. That's probably where the majority of this is coming from. The area of that section was 9.71. So the D distance is the distance from this guy to this guy's down here. So the easiest way to do that would be take half of that plus a half and subtract it from that. So half of that plus a half, because we're coming up there. Some people would forget to do that, but you're actually coming from that point. So a half plus a half of that minus that. So that gives you a D value of 1.495. So we're going to square that, multiply that, and we get 21.702. So we add these together, and we get 192.702. So notice there's a lot of stiffness coming in from that plate because it's separated so far out. So let's see what's happening to the lower plate. So for the lower plate, we have shape 3. His moment of inertia is going to be base is 12, height is a half. So it's going to be 1/12 the base times the height cubed. Well, 12 divided by 12 is 1, so it's basically just height cubed, and this turns out to be not much. So you're not getting much stiffness from the actual shape itself. 12 times a half gives me an area of 6. So the D distance is the distance from here, the composite area, composite XX, to the shape's XX. So basically you're just taking a quarter from that. So if we subtract a quarter, what we get is 6.61. Square that times the area, that gets you 262. So because that thing is separated so far away, even though the plate shape itself and the way it's oriented isn't giving you a lot, you're getting a lot here. So we add those two, and what we ultimately come up with is 262.278. So when we sum this column, we come up with a grand total of 66582, essentially, inches to the fourth. So this would be the IXX. So that's got a lot of stiffness. So let's see what happens when we load it this way. So we're looking at loading it this way or this way, and that's what this is. Now we're going to load it this way or this way. So again, we're going to have shape, IY, area, D, which now we're looking in that direction, A, oops, that's just AD squared, and then ultimately my IY value. Okay, so for shape 1, now we're looking at shape 1 in this direction. So what's happening? This is the base, this becomes the height. So it's 1/12 the base, which is 1 times the height cubed. So we're basically looking at 14 cubed divided by 12 gives me 228.667. Area is 14 times 1, that doesn't change. Notice it doesn't matter which way you're looking on it, area is area. Now, interestingly, what's happening? The midpoint of this, the midpoint is coinciding right with the y-axis, so D becomes 0. So therefore, this is 0. So all of your stiffness is just strictly due to that. There is no separation. So in this case, no distance, that's what you wind up with. So for shape 2, we have an IY, which is our I-beam. That was determined to be 36.6 from the chart. Also from the chart, we got 9.71. And again, the centroidal YY of the composite is running right down the centroidal YY of the shape. So D is 0. 0 times that squared is just 0. And then you wind up with 36.6. So the last shape, shape 3, is our plate. Again, we're looking this direction, so this is the base. Base times the height cube divided by 12. So basically it's 12 cubed divided by 12, and that becomes 72. Area is 6. Again, these are coinciding with each other, so no distance. 0 squared times that is 0, and you just wind up with 72. So when we do the sums, we get 337. It's a 7.27, essentially inches to the 4th. This would be our IYY value. So from a standpoint of loading, you get more rigidity when you load it this way than if you load it this way. In fact, it's almost twice as much. So that's what we're after.